Let's talk about systems of differential equations. So a matrix A is any rectangular array of numbers or functions. And you can see that like A11 is in the top left. The subscripts indicate which row and which column it is. The first one is the row and the second one is the column it's in. So for example, AM2 is in the mth row and the second column. Size of a matrix is m by n, where rows is always first. A square matrix is any matrix that is an n by n, so same number of rows as it has columns, and a column matrix is just a matrix that has m rows in one and only one column. Two matrices are equal if each of their entries are the same. So A sub ij is equal to B sub ij for all I and j. So in the examples I have written down, the matrix A is equal to matrix B because they are the same entries in every single location. But B is not equal to C because they differ in one and only one spot. If you differ in one or more spots, then you are not the same. And for example, A is not equal to D either because D is a different size. D is a 2 by 3 matrix and A is a 2 by 2 matrix. So they can't be equal to each other if they're not even the same size. You can take a multiple of a matrix A, it's called the scalar multiple. So for example, I did 3 times A, where A is the matrix up here in number 5. So I did 3 times 2 is 6, 3 times 1 is 3, 3 times 4 is 12, and 3 times 6 is 18. So you just multiply every single entry by that scalar k, which you can see I distributed that k onto every single one of these guys inside. If you want to take a sum of two matrices, you're just going to add your corresponding entries. So I took A plus C in the previous example. So this 4 came from 2 plus 2, the 2 came from 1 plus 1, the 8 came from 4 plus 4, and the 13 came from the 6 plus 7. So you're just adding the like entries. If you want to take a difference of two matrices, it's the same as A plus a negative 1 times B. That's what it is by definition, but it's just take the entries of A and subtract the entries of B. Matrix multiplication is probably where it gets a bit more exciting, so we've written it down here in full definition form, but what it really means is you're going to take the first row and dot product it with the first column, and that will give you the entry in the first row, first column is the idea. So whichever row you take, that's going to be what row it is in the product, and whatever column you take, that's going to be the column it's in down there. So let's take A times B, where I have these two right here. A is a 3 by 2 matrix, and B is a 2 by 3 matrix. Sometimes you can't actually multiply matrices. The thing that has to match is these guys. If those don't match, you can't multiply them together. If you can multiply them together, in this case I can because I got those 2's there, this is going to be the size of the resulting matrix. So I'm going to get a 3 by 3 matrix when I'm done with this multiplication. So let's actually do this. So I have 2, 3, 1, 4, negative 2, 0, multiplied by 1, negative 1, 2, 0, 3, 1. So I'm going to take the dot product of the first row with the first column, and that's going to give me the entry in the first row, first column of my product. So I'm going to get 2 times 1 plus 3 times 0. Next one, I'm going to take the first row and dot it with the second column. That's going to give me the entry in the first row, second column over here. So 2 times 1 plus 3 times 3. And let's see, what color haven't I used yet? Black. Perfect. First row, third column is going to give me the entry in the first row, third column, which is 2 times 2 plus 3 times 1. Repeat these thoughts now with the second row. So I get 1 times 1 plus 4 times 0. 1 times, is that a negative 1 in there? Did I miss the negative up here? Looks like I did, that's negative. Plus, what was I doing? 1 times negative 1 plus 4 times 3. That's what I was doing. And then a 1 times 2 plus 4 times 1. And then the third row, first column is negative 2 times 1 plus 0 times 0. Third row, second column is a negative 2 times negative 1 plus 0 times 3. And then the third row with the third column is a negative 2 times 0. Oopsies, a negative 2 times 2. There we go. Plus 0 times 1. I think I got that right. Everything from here is going to be simplification. So we'll get a 2 plus 0 is 2. A negative 2 plus 9 is 7. A 4 plus 3, 7 again. A 1 plus 0 is 1. A negative 1 plus 12 is 11. A 2 plus 4 is 6. A negative 2 plus 0 is negative 2. a 2 plus 0 is 2, and a negative 4 plus 0 is a negative 4. So you can see I get a 3 by 3 matrix when I'm done. So that's a little bit on matrices. So 10.1 is all about just some examples of where systems come up. You should read it. It's pretty cool. But we're going to jump into 10.2 next, which is, well, what is a system of differential equations? And we're going to talk about linear ones. So here's what they look like. I'll let you read through all that. All those A11, Y1, those are all subscripts. But your unknowns that you're trying to find are essentially these y's. So y1, y2, all the way through yn. Those are the things that I don't know. I do know all the f's, I do know all the a's, and the left-hand side are the derivatives of those unknowns. So if you can write it like that, that's called a linear system. You can write it in matrix form. You just make the left side one big matrix, and then here, that first row again, when you think about matrix multiplication, you take a dot product of this with that, which is how you get the A11 Y1 plus A12 Y2, etc., for that top row, which is kind of what I was saying out loud was this guy. And then plus, you just add the corresponding entries, which you get there. So we call this matrix on the left, that Y prime. This guy is our A matrix. That, again, is our Y, just undifferentiated, and that's F. And bold indicates vector or matrix for you. Okay? So, yeah, there you can see the Y, A, the F is right there. We call A the coefficient matrix. F is the forcing function. A and F are continuous if their entries are continuous. And if you get F is identically 0, means you have a homogeneous system, which looks like the following. Y prime is equal to AY versus a non-homogeneous is Y prime is equal to AY plus F. If you get initial conditions, it looks like that vector evaluated at T0 is a K vector. So your K is equal to essentially some K1, K2, all the way through Kn, where Y1 of T0 is equal to K1, Y2 of T0 is equal to K2. Okay? The existence of a unique solution, you'll have a unique solution when the coefficient matrix A and the forcing function are continuous, and your initial condition T0 is somewhere in that interval. Then you can have an arbitrary initial condition set up, and then this guy has a unique solution. So yay, things are just continuous. So let's try and put the following in matrix form. So my y vector is going to be just the unknowns. It looks like I have two unknowns, y1 and y2. And then my a are going to be the coefficients on those. So it looks like I have a 4 attached to the y1 and a negative 7 attached to the y2 for the first y1 prime. In y2 prime, I have a 5 attached to the y1, and I don't have a y2, so I'll put a 0 there. And then the forcing function is going to be all those things that don't have a y1 or y2 attached to it. So that's 6t from the top and a 4e to the t from the bottom. So with those, this then looks like y prime is equal to ay plus f, where the derivative of y is just differentiate individual terms. This one down here looks like I have 3 unknowns, y1, y2, y3. And my coefficients on those looks like a negative 3, 4, no y3, 5, no y2, 9, no y1, 1 y2, 6 y3, and then my forcing function is the things without that, so e to the negative t sine of 2t, 4e to the negative t cosine of 2t, and negative e to the negative t. So solution looks like a vector where you figured out what's the y1, y2, all the way through yn, and just to emphasize again, these are all functions of t. They better be differentiable, and they better satisfy the actual dE. So let's verify that the following is a solution to that guy. So the left-hand side of that dE is y prime. So the left side, which I think I already said, is just going to be the derivative of what I'm given. So I'm looking at the original, and it looks like I'm going to need the product rule. So 5e to the t cosine of t is if I differentiate the first, and then minus 5e to the t sine of t. Second one is a 3e to the t cosine t minus 3e to the t sine t minus e to the t sine t minus e to the t cosine t. So that's what the left side looks like, which is the y prime. And if I take a times y, which is the right side, this is a negative 2, 5, negative 2, 4, times y, which the size of y, it has 2 rows and 1 column, despite how big that second entry looks. Still 2 rows, 1 column. So when I do this multiplication, the first thing I'm going to do is I'm going to take this first row of A and dot it with the one and only one column of the Y. So this is going to look like a -2 times the top entry will give me negative 10 e to the t cosine t, and a 5 times that second one is a plus 15 e to the t cosine t minus 5 e to the t sine t. And then if I do the second row, dot it with the one and only one column, I'll get a -2 times that first entry is a negative 10 e to the t cosine t, and then 4 times that second one will be plus 12 e to the t cosine t minus 4 e to the t sine t. So if we go back and look, now let's see. So I have a negative 10 e to the t cosine t plus 15 e to the t cosine t. That's the 5 e to the t cosine t. And then the minus lines up. So those first entries are the same. And then let's see, what do I got for the second one? So we have negative 10 e to the t cosine t plus 12 e to the t cosine t. That's 2 of those total. Up here I have 3 minus 1. That's 2. And then minus 4 e to the t sine t. Looks like I got minus 4 e to the t sine t. So since those two matrices are the same, that means y prime is equal to ay, which means it is a solution to that DE. System of DEs. Moving on to 10.3. Again, we say y prime is equal to ay as a homogeneous system. If y is identically 0, that's the trivial solution. It is always a solution to the homogeneous system. If you have n solutions, which are vectors, and c's are constants, then we say that that linear combination where you just multiply each one of those by constants and add them up is a linear combination of them. If you have found n solutions of y prime is equal to ay, then that linear combination of them is also a solution. And we say that that y1 through y1 is a fundamental set of solutions if every one is a solution and every other solution that you could possibly find is written as can be written as a linear combination of those n that you found. It's a fundamental solution set. If you do have a fundamental solution set, then the general solution is just we'll take a linear combination of them. So it's all like we're used to. We just have a bunch of them now instead of one of them. And that set, y1 through yn, is linearly independent if the only constant c1 through cn such that c1y1 plus c2y2 plus all the way through cn is equal to the 0 vector for all those t's in a to b. Are those 0 constants, as in they have to be constants to make that work? Then we say it's linearly independent. Otherwise, we say they're dependent. So let's say you have an n by n matrix. It's a square matrix. Then a set of solutions, y1 through yn, is a fundamental set of solutions if and only if it's linearly independent. And we can test to see if they're linearly independent by taking the Wronskian, which means if you're going to take the Wronskian of these n functions, we load them in as columns of this matrix. So y1 is the first column, y2 is the second column, etc., through yn is the nth column. As long as that thing is not 0 for every t in there, then you got linearly independent ones. And again, since we're working with DEs, things are nice. The Wronskian is either identically 0 or never 0. So let's use these thoughts to verify that y1 and y2 is a fundamental solution set of y prime is equal to ay, where I have the a, the y1, and the y2. So a couple things we need to show. One, we need to show that they're actually solutions. And then 2, we need to show that they're linearly independent. And then 3, that that linear combination of them satisfies the initial condition. So first things first, let's show that they are solutions. So we're going to show they are solutions. Let's start with y1. So y1 prime should be the left side of that DE, and y1 prime is 6e to the 6t, 6e to the 6t, and then ay1 is equal to 2442 times e to the 6t, e to the 6t. So dot product the first row with the first and only column. I'm going to get 2e to the 6t plus 4e to the 6t. And then the second row with the first column gives me the entry in the second row, first column, which is 4e to the 6t plus 2e to the 6t, which you can see that is the same as the y1 prime. They're both 6e to the 6t. So y1 is a solution. That's what I've shown so far. y2 prime is going to be a negative 2e to the negative 2t and a positive 2e to the negative 2t. That's the left side. and then A times y2, which will be the right side, is the matrix 2, 4, 4, 2 times e to the negative 2t, negative e to the negative 2t. So this is equal to 2e to the negative 2t minus 4e to the negative 2t. That was the dot product of the first row with the first column. And the second row with the first column is at 4e to the negative 2t minus 2e to the negative 2t. And again, you can see my first row is a negative 2e to the negative 2t in both cases, and my second row is a 2e to the negative 2t in both cases. So that means y2 is also a solution. So I've shown their solutions. Now I need to show they're linearly independent, so I'm going to take the Wronskian of y1 and y2. So I'm going to take the determinant of the matrix whose first column is y1, so e to the 6t, e to the 6t, and whose second column is y2, which is a e to the negative 2t minus e to the negative 2t. Determinant of a 2 by 2 matrix is the product of the main diagonal, so e to the 6t times a negative e to the negative 2t is a negative e to the 4t, minus the product of the off diagonal, which is the e to the negative 2t times the e to the 6t, which is also an e to the 4t, so I have minus 2e to the 4t. This is never 0, because it's exponential. But what this tells me is that they are linearly independent. What that means is the general solution, y is equal to c1 y1 plus c2 y2, which is a c1 e to the 6t e to the 6t plus c2 e to the negative 2t negative e to the negative 2t. That's my general solution to the DE. And now the last thing we're going to do is we're going to find the one that satisfies the initial condition, y evaluated at 0 is a negative 3, 9. So what I'm going to do is I'm going to plug this in. So y evaluated at 0 is a c1 times e to the 0, which is 1, e to the 0, which is 1, plus c2 times e to the 0, which is 1, and a negative e to the 0, which is negative 1. That should be equal to a negative 3, 9. If you'd rather write this in a form you're used to looking at, this first column matrix, that's the word I'm looking for, is you just distribute the c1 onto both of those and distribute the c2 onto both of these, and that should be equal to negative 3, 9, and then you take a sum of these and you get c1 plus c2 and a c1 plus a negative c2. That should be equal to negative 3, 9, which means you should have c1 plus c2 is equal to negative 3, and c1 minus c2 is equal to 9, which might be a form you're a little more used to working with. If I add those two together, the c2's drop out, and I know 2c1 is equal to 6, which means c1 is equal to 3, which means what? c2 is negative 6? I think that sounds right. So my solution to that initial value problem is c1, which is 3, times e to the 6t, e to the 6t, plus c2, which is a negative 6, times e to the negative 2t, minus e to the negative 2t. That's the end of 10.3, and on Tuesday we are going to learn about how to solve these things.